of those people who sticks firm to my decision once it's been made. For me, it was to do research in oncology. My mother had cancer when I was in high school, and I was sure oncology was my path. But then, in one moment, you suddenly realize you want to turn in another direction. I'm Linda Zhong-Johnson, and I'm a graduate student in microbiology at MIT because I had that moment, and I turned in a different direction. Right after I graduated from the University of Toronto, my mother took me on a cruise to Alaska to celebrate. And what I saw in Alaska just blew me away. I grew up in Hangzhou, China, and the rivers and streams I was used to seeing looked like this, rather polluted with plastic trash. When I immigrated to Canada, it was obviously much better, but you can still find plastic trash along the riverbanks. It never bothered me, it's just the way it was, the way I was used to seeing things. Pollution seemed like the natural part of life. But on that trip to Alaska, I saw this pristine and beautiful scenery. It was so clean, so clear, it was inspiring, and it just hit me. This is the way our environment is supposed to be. And then I realized, okay, you know what? Everyone works on cancer research, and that's really great. But perhaps they don't really need me. If I want a better world, the problem I need to solve instead is figure out how to get rid of plastic waste. Because yeah, you can try to recycle this water bottle, but basically all that does is delay when the materials end up in a landfill, or worse. The materials are lost, and we have to make new water bottles from petroleum. We ultimately add more plastic waste every year with the recycling strategies we have. We need a better one. And I also noticed there weren't many people working on the problem of how to degrade plastics using biology. So just like that, I changed the course of my life. I applied to MIT Microbiology because of the interdisciplinary program and the range of professors at MIT interested in solving problems using biological engineering. For one, Professor Sinskey actually pioneered the field of biodegradable plastics back in the day. So, for the non-biochemists out there, what that means for my research is figuring out ways to use enzymes, these little proteins that speed up chemical reactions, and finding ways to use enzymes to basically eat up and break down a material of some kind. It works by attacking the polymers, the long strings of repeating units that form the material. With the right enzymes, you essentially disintegrate the original substance. Say you splash some gravy on your blouse or some red wine on your slacks. The polymers in a stain like that are short. There's lots of space between the polymers and they're accessible to water and thus to enzymes. So when you use your enzymatic laundry detergent on stains like that, the enzymes get in there, chew up the stain, and don't harm the fabric. And your stain is gone. But it's much harder to do when the product is entirely made of insoluble polymers, such as PET plastic or polyethylene terephthalate, which is the type of plastic I'm studying. That's the plastic you find in water bottles and takeout containers and those clamshells your cherry tomatoes came in. That plastic has polymers that have hundreds of repeating units, and there are many, many, many of these polymers packed tightly together around themselves. There's essentially no space for an enzyme to get into, and no water in between the polymers. If the plastic product is meant to hold water, that's a pretty great characteristic. But it's a terrible characteristic if you're trying to disintegrate the bottles using enzymes. The only point of attack is the surface of the material. So I thought when I first started that all I really had to do was find the microbes that break down PET, because microbes are amazing and can adapt to eat all sorts of food, and harvest the enzymes that broke down PET. From there, we could recycle and reuse its components to make other products. No more landfills stuffed with these bottles and food packaging. It was such a compelling idea. Good thing I had no clue then how hard this problem would be to solve. Because here's the thing, scientists know that enzymes can catalyze all sorts of chemical reactions. We know that the hotter the reaction, the faster they work. But enzymes are fragile, and if you raise the temperature too much, even by 1 degree, they unfold, essentially falling apart and losing its activity. But incredibly, we don't know how most enzymes actually work. We don't know the mechanism of the reactions. Most enzymes don't work at all on solid substrates because they can't penetrate polymer strands to get in and do their thing. So that's a problem if you're trying to break down PET water bottles and the like. To target and engineer the right enzyme to degrade the plastic quickly and cheaply enough to be commercially viable, there turn out to be 2 paths, and I'm working on both of them. The first is to create a random library of thousands to millions of enzyme variants and look for ones with improved characteristics. That requires a high throughput screen, essentially the ability to test thousands to millions of enzymes in a short amount of time. Without that screen, you can be testing your library one by one for the next century or so. It's a needle in a haystack problem. The second path, create a set of biochemical assays to measure the physical characteristics and mechanism of enzymatic PET degradation so we know how specific enzymes work. Then we can target our engineering efforts. I was able to develop one assay before the pandemic hit, which allows me to study variants of PET degrading enzymes and understand how different mutations are affecting enzyme behavior. Essentially, I'm deciphering where we made the enzyme better and where we made it worse. As of now, I'm discovering that some mutations aren't doing what others thought they were doing. Other researchers started looking at reactions after 18 hours. But with the new assay, I'm looking at it starting at 30 minutes. And that is important because the reaction starts right away, and you need to measure that too. So even in the midst of a pandemic, even when I can't do much of what I've been wanting to do, I still have tools and resources to work the problem. And we're getting closer to the answer. I'm grateful to be at MIT where we have the resources and the mandate to keep exploring. And the water bottles and lettuce containers you have at home, we know that they're not going away because manufacturers know they're good solutions for their products. And that's okay. My hope is that in the not too distant future, your plastic recyclables become truly recyclable, truly reclaimed and repurposed because of the ways we've come to understand the enzymes and apply them. That's the better world I see for all of us. Thank you.